My name is Darren Broderick. I'm a senior software engineer at Liberty IT, and today I'm going to show you two things: TensorFlow with Keras, and we'll make a simple neural network. We'll define a model, compile it, fit it, and then train it, and then we'll run a prediction on an algorithm just to see how it behaves and what kind of metrics we can get from that. And then I'll look at showing everybody AI bots called Jenkins, which is to play rock, paper, scissors. And it's again using Keras, but it's using a pre-trained neural network called SqueezeNet, and we'll add our own data into that. So let's get started, and you'll see me later on just getting some real estate. What we have on the screen at the minute is just the imports, but these comments are just to kind of guide us for what data we're going to feed in. So here we have all of our input data, which is going to be our X values, and the predicted data will train off what we give it as Y, and the relationship between the two is that 2x minus 1 is the linear straight line relationship that gets x to y. And we will run a prediction. From given an x value of 10, we would expect a value of 19 to be given back. However, the model will leave some room for error in the possibility that if more data was fed in that wasn't a 2x minus 1 relationship, that it had to be certain of that. So you'll get a value of roughly 18.999, and that's just the way the model will be trained to combat that. So we want to start with a simple model, and what we'll pass in here is using a sequential layer, and all I've put in here is a unit of 1, which is just a single neuron, so this is the simplest we can make it, and an input shape of 1, because all we're feeding it in is values of x. So you can see this kind of as our training data, and this is our result of that. So I'll draw a wee diagram later on as well, just to kind of highlight how these two are working together. So the model here is, this is really it for your model design. The rest will start to be what kind of optimizer we use and what way we'll compile it. So let's write that now. And our optimizer is just written through TensorFlow again, and we'll just provide it here. SGD. And what we're able to do now with these optimizers, we'll also add in a loss function, and both of these are functions in themselves. So the optimizer lets us be able to actually generate a guess every time we give it a value of x and a value of y. It's trying to guess the relationship between them. So each time it will do that and try and get a bit smarter. And then we can also add training parameters like learning rate, which is a good default to have, is 0.01, and that just decides how much of each training we want to add on to the weights, how quickly we want to smarten our model effectively. Okay, so the SGD is the stochastic gradient descent, which is just a popular optimizer to use, especially for simple models like this, because it gives good performance. And then we just want to compile our model, so we won't be able to add in our loss function or get any metrics out of it. So our loss function is another very popular one, mean squared error. And what it will do for us is enable to give us the squared error difference between what is true and what is predicted. So we know the true values are y, and if it predicted this to be 3.1, the difference between the two is what will come back as a metric. And it's just a sign of how smart or how much improvements the model is making. And again, we'll provide the optimizer, which we've already defined above, and that'll feed in that learning rate as well. So next we have to give it the data, which we have at the top. We're just going to provide it now in an actual array and give it the correct data type of float. So I'll grab it here, just set it up. This is our x values. It's a data type of float. And then we'll do the same for y as well, and just feed in what our true results are. Okay. And then all we've left to do is fit, which is, I'll write it out first here. It's a way of saying fitting these x values onto y, and effectively how many times we're going to loop over. So we'll do that 1,000 times, which will run pretty quickly, but it gives us a good indication of how smart a simple model can make. And this is just going to be trained off our CPU on the laptop here. There's no GPU behind the scenes or EC2 instances running or any heavy loading stuff. This is just straight off the Mac's own personal power. So that's everything we need. And if we run it on the side here, what we're going to see is all the epochs running through, and 1,000 barely took a few seconds. And from that we can see the models finished 1,000 epochs for one input, and this is the time per step, so it's extremely small numbers of milliseconds. So what we're trying to see here mostly is that the loss gets closer and closer to zero, and again, once you start to scroll up, you can start to see that it's 1 here, but it's starting to go into 10, just to show that it's getting even smaller and just making a more confident prediction on that. So let's see what prediction we'll actually get if we provide it a value of 10 and see if we get close to 19. And we'll just retrain it as well. It only takes a second. So and we get a value of 18.999903, and that's all we're doing there to show that very easily you can make a simple model. You can give it these kind of metrics, and in just a few lines you can train something that can actually run a prediction and go through that 1,000 times. So what are we really doing behind the scenes? We've got 3 layers. So we have our input layer, which is what we just provided as our x, and then we've also shown that we're given y just to show that that is the correct relationship of what x will be. Then we pass that into a hidden layer, and that will go to an output layer, which is the prediction. And then these are all the different types of weights, as they're called, which are all the different options the neural network has to train itself and decide what actions to take. And those are all those steps we'd seen in our terminal there. So as it starts to feed into different neurons, some will start to become more popular than others, and eventually they'll all feed into a prediction and start to either get smarter, or if things aren't going up in accuracy, it will start to just drop some of these and run more iterations to become smarter. So this is our input, this is our hidden layer, and it's a layer you don't get to see because that's where the neurons sit and become smarter to do so. And then our output layer is our prediction. And that is all I'd hope to show for the TensorFlow side of things on Keras, just showing that a model can be made very quickly, and you don't have to provide a crazy amounts of data as well just to get it showing something. So we'll bounce on to the rock, paper, scissors, and this is a bit more hands-on because we'll need a lot more data to control the neural network to just make smarter information, because it's now taking images as our data. So there's a lot more happening here. So I'll just walk us through what each step is. So the first thing we're going to want to do, and this is kind of true for any machine learning problem, is you're going to want to collect your data. So I ran a script for that, and all of this is using just OpenCV, and I'm going to be collecting images. Let's say I want to collect paper. Okay, so collect about 150. You just want different types of paper to start to think about how you're going to handle different biases, and it will push it into a folder called data. And here you'll just see tons and tons of pictures of my hand making the paper gesture. But what you'll want to do is start to think about, as we're talking about bias, do you want 150 pictures of just your hand? So you'll start to think about how do you collect different images from different people, different types of lighting, which is also really important, and also with the way the camera's moving, if there's any images that are blurred, that's another important thing that you'll want to start to clean up and just remove from your data. So that's step one, and that's all that's needed there, is just to collect the data and size it in a way that the neural network expects. So for me it's 350 by 500, and you can have that any size, but it's just to be consistent. Okay, so the next thing we can do is train the data, which is here, train the model. So I'll not run this because it takes about 10-15 minutes to do so, but I wanted to show how the similarities between what we had seen in TensorFlow and what this guy has as well. So this will look familiar as well. It's just another compiler using a different optimizer and a different learning rate, and all we're adding in is a metrics for accuracy, because now we have something to compare to based on a prediction of all the data I've collected for rock, paper, scissors, and noise, as I call as the background data. All of these get labeled now to all rock images are 0 indexed, papers 1, scissors 2, etc. And we're just saying that now if you see a label that looks like rock, it's now 0 to you, and that's how we'll train our neural network that way. And so this is the heart. This is some of the things we've been different. I have lots of notes here as well, because if this is all on GitHub for free, or just open source, just for anybody who needs it. And the SqueezeNet is what our internal neural network is being trained for. So the SqueezeNet is important because it's previously trained and it's available as well for everybody to handle image classification, but we just want to put layers on top of that to manage the data that we have, so that we control what gets trained and what neural network this will start to identify off our hand gestures. A few other new things that we haven't seen before is dropout, which is really, really important and helps prevent overfitting, because what it's effectively doing is cutting half of its learning, and that is to help generalization. It can get misconstrued that it helps bias, but bias isn't removing data. Bias is having a good set of different data. So you're really focusing dropout to be the point that you're looking at your model not seeing the same images over and over again, seeing a good variety of your images, but your bias comes from how much different types of data you have behind the scenes as well. So I find 50% is really good. I've seen 80% very common as well. If you're training enough times, it doesn't matter how much you're dropping, because you're always going to be feeding more information into the network as well. The activation value and the global average pooling 2D, these are just things I found that have to be standards for like image classification, that has helped me just get a much better model that can actually recognize my gestures, which I'll show in a minute as well. And what we're trying to do is handle 4 images, so that we have rock, paper, and scissors. The background is very important because it's our type of noise, and if there's no gesture played, it's really important that we decide that nothing's being played, and that background is what's holding back the neural network from making a move as such, saying that rock's been played but nothing. It's just a background. Okay, so, and that's really it. All we're doing is just looping through the data, but the big inputs are what your compiler is, and there's our fit again as well. And although we looked at 1,000 epochs before, the data is a lot more detailed here, because we're looking at the types of features between the images, so it just takes a long time to train that as well. But once you do have it trained, and again in the project I provided a trained model down here called example RPS model 1, and that's the one I'll be using, and it works pretty well against me, but I'll be interested to see if it works well against others too. So you can run and do, you can test your images as well from a small script in here, and I've provided test images here. So for something like rock, which is again is just my hand, but you can just for fun, or you can be curious to see if you try other things that look like rock, what do those come out as? So you can get a bit lucky, and I've got a few images here. You can maybe get lucky that it will predict rock, but if you show it something it's never seen before, it's really it's almost a random guess it'll throw out. Like I would have said that looks more a bit like a scissors, maybe one of the blades, but it's decided it's rock, and that's where you can maybe start to think about, okay, well, maybe if I provided this as noise background, I would prefer if that said none, this is none of the three, and don't do anything, because that's not one of the three gestures I need to be a part of. And once you've done those three, it's time to play the game. So here's the game in all its glory. I'll line myself up. I've had a few rules to the top and a best of 3 score. So you can see, turn the light on as well, as it gets a wee bit dark. It's maybe not used to this type of shade. It's maybe used to a bit brighter where I've collected data maybe at midday, but it's a good example of how it's thinking something's being played. But generally, if I pause it here at the right moment, generally this should be waiting, Jenkins should be waiting for your move. And let's see, if I unpause it and I play rock, so paper, so J for Jenkins wins, paper, Wolverine, ooh, almost, sort of. Is any happier there? Much happier there. You get the idea. And then scissors, a bit more confident with scissors, a bit more of a defining feature. But that's Jenkins, that's what he's up to. And now you can just hit restart game, or you can play through. I thought that was just good for competition standards. And it's been really fun to build something like this. I was able to play it with work, and this is how it was done. It was a computer, Mac webcam playing through, I'll just minimize this guy, playing through to Teams calls, person sharing their screen so they can see Jenkins, and then Jenkins can see their shared webcam. So it didn't work terribly well. It got maybe 33% accuracy, and I really understood that I should have collected a lot more data from the scenarios it was meant to be playing in. So although it's good against me here, this whole environment is what it was trained on. I tried to understand that maybe if I blocked the webcam a wee bit, try to like darken a few things, get at different times of night, but it generally had lots of trouble with that, and I realized that maybe instead of a couple of 100 images, I should take the time and put thousands and thousands of images in, and especially different levels of backgrounds, so it doesn't like have this kind of like flickery effect. So that's why I tried to add this pause feature, just to kind of get a still shot to see if I could find any weak points in it. And that is everything to me. If I've got time, I'll show you. Load up this guy again, GitHub, and there's a Medium article as well. So I'll look for Twitter too. So rock, paper, scissors. Yep, so it's here as well for everybody. There's a Medium article too on it, and my Twitter as well if anybody is interested in any of those things. There you are, and thank you very much. If there's any questions during the live chat, I'll be happy to answer. But thank you.